All right, welcome back. This is the end of week 2 in CS50, and this is an excessive amount of what's called ASCII art. People who have spent way too much of their free time actually sketching out most of the scenes from Star Wars entirely in their own ASCII character code. So this is a bit of an animation that's a bit of an internet meme these days and goes around, but we've linked to it on the course's website if you'd like to watch the whole film later. We thought we'd begin, though, not just with ASCII art, but with something a little sexier than that, that paints the picture for this week's and next week's problem domain, that of cryptography and security more generally. Some of you might have seen this actual film before, one of my favorite excerpts of which is this one, that one too, is this one here.
What's going on? What are you doing to my daughter?
Permit me to introduce the brilliant young plastic surgeon, Dr. Philip Schlotkin, the greatest nose job man in the entire universe and Beverly Hills.
Your Highness.
Nose job? I don't understand. She's already had a nose job. It was a sweet 16 present.
No, it's not what you think. It's much, much worse. If you do not give me the combination to the air shield, Dr. Schlotkin will give your daughter back her old nose.
No! Where did you get that?
All right, I'll tell.
No, Daddy, no, you mustn't.
You're right, my dear. I'll miss your new nose, but I will not tell him the combination no matter what.
Very well. Dr. Schlotkin, do your worst.
My pleasure.
No! Wait! I'll tell.
I knew it would work. All right, give it to me.
The combination is 1, 2, 3, 4,
5. So the combination is 1, 2, 3, 4, 5.
That's the stupidest combination I ever heard in my life. That's the kind of thing an idiot would have on his luggage. Thank you, Your Highness. What did you do? I turned off the wall. No, you didn't. You turned off the whole movie. I must have pressed the wrong button. Well, put it back on. Put the movie back on. Yes, sir.
Let's go, Arnold. Come, Gretchen. Of course, you know I'll still have to bill you for this.
Well, did it work? Where's the key?
It works, sir. We have the combination.
Great. Now we can take every last breath of fresh air from planet Druidia. What's the combination?
1, 2, 3, 4, 5.
1, 2, 3, 4, 5.
Yes.
That's amazing. I've got the same combination on my luggage. Prepare Spaceball 1 for immediate departure.
Yes, sir.
And change the combination on my luggage.
So if you'd like more of that, that is a classic called Spaceballs. And we have another little classic for you in a little bit. So you might laugh, but odds are, statistically, some of you in this room has a password that's not all that dissimilar from 1, 2, 3, 4, 5. And some of you might even have Post-it notes back on your desk. So 1, 2, 3, 4, 5 is clearly insecure as a password. One, because it's just so easy to guess. Even you, if you're trying to break into someone's account, you might try simple things like that, or the ever popular password, or something similar. But in reality, what systems typically do, even if a password is weak like that, they're actually store, computer systems, things like this. So if you've ever forgotten a password on a website or one of Harvard's passwords, and you're told by some IT person that they cannot, in fact, tell you your password, but you can change it, that's generally algorithmically correct. For security purposes, passwords are typically not stored in computers in so-called clear text, but rather in ciphertext, in some kind of encrypted fashion that looks mostly like random nonsense. But the reality is that that is the result of applying some mathematical formulas to the original password, 1, 2, 3, 4, 5, the output of which is something crazier looking. The idea being, if you see the crazy looking thing, it's not all that easy, if at all possible, to figure out what the original password actually was. So in short, when you create an account on some new website, Facebook, Google, any of these sites, they're storing in a database your username, and that's generally in the clear, or your email address, but then your password is encrypted. But this seems to beg a question. The next time you log in, time number 2 or 3, how in the world does Google or Facebook or Harvard know that you've typed in the right username and password if they too no longer know what your password is? It seems like once you've encrypted the password, you're kind of screwed because you no longer remember what the new one is if this is all you're storing. So what could you do? What are some options? OK, so you could decrypt it. So decrypting is just the opposite of encrypting. The problem with decrypting it is that if you're going to decrypt something like this on an automated fashion, well, that means that the web server or Harvard server itself needs to know how to decrypt it. And generally, encryption works by having some secret password or special key that only the website's owner knows. So if you wanted the website, like Google or Facebook, to automatically decrypt this and then compare your password, well, the implication is that then the website's password or key with which to do that decryption has to be stored somewhere in the server. So this then implies that if some bad guy breaks into the server, not only can he or she steal the crazy looking stuff like this, which is mostly useless, but if they have access now to the server, they can steal also whatever trick you're using to decrypt these things, because that's got to be implemented in source code, right? Whether it's C or some other language. So it's really not helping you if you've actually encrypted these in that fashion. Yeah.
Encrypt what you put in and then check it against what it has stored?
Yeah, exactly. So that's a nice solution here. So if the server is only remembering the ciphertext, and actually let me tweak my wording now. Though it's very similar in spirit to encryption, a better word for this would be a hash value, H-A-S-H. And a hash value is generally the result of encrypting something and essentially throwing away the key, though the mathematics are a little different than that. In other words, when you take a hash of some input, the result is some hash value, and statistically it should be impossible to reverse that. So it's one-way encryption, if you will. So that's OK, though, because if Facebook and Google are storing this as the king's password, well, that's fine, because the next time the king logs into this website, he types in his username, he types in 12345, hits enter, but then all the website has to do is take another hash of that input that is run 1, 2, 3, 4, 5 through the same algorithm, the same mathematical formulas. And if the output of that process matches the output of the original process, well, then you can assume that, OK, he must have typed in the exact same thing. So this is why IT people can't tell you your password, but you can continue logging in. They can't tell you it because this encryption is one way. It's taking the so-called hash of the original input. And this is for security purposes, because, again, it means if some bad guy steals all of this from your server, physically steals your server, breaks in over the internet, takes your whole database, they might have your usernames and your users' email addresses, which is perhaps bad for privacy. But at least they don't know your users' passwords because those are at least encrypted. And these days, if you read in the mass media or see on CNN some story about some website being hacked, the likes of Sony or the like, where their users' databases are stolen and you suddenly have to change your password, that is often because these companies, amazingly, aren't even doing something simple like this. There are numerous cases of companies, actual legit companies, storing users' passwords in the clear, just as 1, 2, 3, 4, 5, or whatever it is they typed in, and then you're screwed if that database is actually compromised. So towards semester's end, when we introduce web programming and MySQL and databases, we'll talk about these kinds of issues because it's actually, amazingly, relatively easy to protect yourself against this. So that's our segue today into security, and now back to C. So with problem set 1, if still tackling it, know that office hours are both tonight, and if you decide to cash in a late day, they'll be tomorrow as well in Lowell. Know that if you've been attending office hours and have had issues with wireless and whatnot, know that Harvard is actually installing more access points in all of these house dining halls for us over the next week or so that we'll have more capacity for everyone, as well as more cookies and the like. Also, if you have any remaining questions with the appliance, there's definitely been some FAQs about like cursors kind of spinning or windows not quite working. Realize we have solutions to all of these problems, so do reach out to us via help.cs50.net, catch me right after lecture, or email me directly in the worst case if you're really pushing up against the deadline. And then lastly, with the appliance too, the only real challenging issues with the appliance is if you have an older computer, 3, 4, 5, 6 years old, or a fancy netbook that's by design very limited in RAM and CPU cycles. But we have a new solution for that too, for the next problem set and beyond, where you'll be able to connect to our servers using a very minimalist program on your computer, not necessarily the appliance. So we'll announce that once details are available. So we should have solutions for all. So here we are, this little song last time, which is kind of itself a little tedious to both recite and also implement. But once you actually have the notion of, say, a loop, which we did, you were able to implement this with, as we saw, like a for loop. So let me go back into this week's source code. This was a file called beer1.c. So following along at home, this is in source directory for lecture 2. And if I go into here, beer1. So what do we now... How did we go about implementing this? Well, we have int main void, that's old hat. At the very top here, how many bottles of beer will there be? And then get int, so that just gets a number from the user. Then recall we had a bit of error checking. Just make sure the user's not messing with us. And in this case, we don't repeatedly reprompt them for a number. We just say, let's just yell at them, sorry, that makes no sense, and return 1. And return 1, again, is the notion like of an error code, an exit code. And then lastly, the actual implementation of this song simply happen down here. Sing the annoying song. So for int I gets n, so if the user types in 99, start counting at 99. On each iteration, subtract 1 from I, and that's what I minus minus denotes, the opposite of I plus plus. And then do this so long as I is greater than 0. And on each iteration of this loop, print this 4-line stanza. And the only thing that's kind of interesting here is this. 1, we have a placeholder for the integer, d, and we're plugging in I, as you can see over here. We have another placeholder that's identical. It's just the English words have changed. This is completely uninteresting because it's just a string, constant string that gets spit out every time. And the interesting aspect here is just this, because the song, again, is 99 bottles of beer on the wall, 99 bottles of beer, take one down, pass it around, 98 bottles of beer on the wall. So we need to somehow dynamically insert I minus 1, but we can do that very simply, arithmetically here. So I minus 1. So the only worry here you might have or should have is, all right, what's going to happen at the corner cases? A recurring theme in programming is you can get 98 cases perfectly right with your code, but that doesn't really matter at the end of the day if you screw up the first case or the last case. And by name, those are typically called corner cases. And so as you start writing your own programs and you start testing your programs by typing in values, well, a program like this, if you type in 5 or 6 or 7 or 97, odds are you're going to get the same fundamental behavior. But things get interesting if you choose those corner cases. Type in 1, type in 0, type in -1, type in 100, type in something distinct conceptually, something that's close to any boundaries you've defined to actually see whether or not something breaks. So in this version here, is there any risk of my printing out -1 bottles of beer on the wall? Will this ever print out -1 bottles of beer on the wall in that last line of printf? OK, so no, it won't. And why? What's the simple protection I've put in place? Yeah, so I has to be greater than 0 according to this, right? So as soon as I is not greater than 0, it is 0, this loop's going to stop executing, which means the value of I itself will never be 0 inside of this loop. The very last iteration will have a value of I equals 1, and so that's safe because we'll say 1 bottle of beer, 1 bottle of beer, ... 0 bottles of beer on the wall, and we'll stop. But of course, if we had done something like this, so I'll go ahead and change this to greater than or equals. I'll save the file. Let me go down to my terminal window here into the source directory, and I'll type make beer1. And now I'm going to go ahead and run beer1 with, let's say, the value 99. Enter. Well, dramatic effect if we now scroll up to see what's actually there. There we go. There's the bug. So now we've introduced the bug, but we had it right the first time. So again, recurring theme, especially before submitting your pset, test these kinds of cases because the TFs are going to be looking for exactly these kinds of things. We're not going to test your program with 3 and 4 and 5 and 6 because most likely those are all functionally equivalent. It's the interesting, the negative numbers, the 0 numbers, the huge numbers that might ultimately be of particular opportunity for your code to break. Questions?